All right, today we're going to look at actually two things. We're going to start with moments, three-dimensional moments, so moments that have maybe a force that's at some three-dimensional angle and it's creating a moment about another point out in space somewhere. So we're going to do that. If you just want to know about the centroids, then that'll happen in a few minutes from now. But we're going to start with this idea of how to calculate moments in three-dimensional space. We don't exactly need that for the centroid material that we're going to do, but it's a kind of small topic. We're not going to spend a whole lot of time on it, and it will help with some of the centroids, and it'll help with other things related to just moments in general. So the idea is that we have three-dimensional space. So let's see if I can find my ruler, and let's build us a 3D coordinate system. I've got my isometric dot paper out so that I can be sort of neat with doing this. So there's the z-axis. We'll put the x-axis here, and then that'll put the y-axis over here. So something like this. Now, in this case, let's build a tube, a pipe, a rod. It doesn't really matter what it is, but we're going to build something right along the y-axis here, kind of like this. Give it some volume, so it's not a tiny little thing. So there it is, and we're going to imagine this point, the origin point, as basically maybe mounted to a wall back here. I'm not going to really draw the wall. I think it would get too cluttery if I did that. But this plane, in this XZ plane, this thing is mounted and sticking off of a wall or whatever. There's a force applied at this end. I'm going to define that force with its X, Y, and Z coordinates. So if it starts here and it's going to come down this direction, and it's going to go down 7. 1, 2, 3, 4, 5, 6, 7. So down here. Going to come down in the negative z direction. Then it's going to come in the positive x direction 8. 1, 2, 3, 4, 5, 6, 7, 8. So something like this. And then in the negative y direction, it's going to go 3. So the force that I'm trying to describe with these x, y, and z coordinates, if I get them in the right order, looks like this. So there's the force, and I'll give it a 150-pound magnitude. Hopefully the dots aren't too distracting with all of the stuff writing on there. And so I've got a point A here and a point B here, and I want to calculate the force, or the moment that this force creates about point B, about these three axes. So it'll have three components to it, the moment will. It'll have a moment about the z-axis, it'll create a moment about the x-axis, and it could create a moment about the y-axis also, although in this case it doesn't. So how to deal with these things. So if this is what you're given, then what you do is, it's similar to what we did with the 3D concurrent force systems, where we found the cosine of the angle between the force and the different axes. We're going to do that same idea again. So this 150-pound force at this weird angle is going to have three components. One of them would be right here. So that would be the x component. It would have a z component that basically is overlapping that blue line there. And then it would have a y component that I'm going to have a hard time drawing because it goes on top of this line. I'll draw it right beneath it. Right under there. So that would be the y component. So if I'm given all of this, and let's make some room on my paper so we can not write on the dots, because it gets really cluttery to write on the dots. So I'm given this, and I want to find maybe the moment created about point B. Oh, can't see that. That says about. We'll go down here. Point B. All right. Moment created about point B by this 150-pound force at the angle that it's at. So this moment about point B is actually, so if we define that as moment about B, it actually is the individual moments, the moment that is created about the x-axis at B. Maybe I should put a B in there. We'll put the B down here. Squared plus the moment about the y-axis at point B and the z-axis. All of those squared. So that's the moment, how we calculate the entire moment. We need to basically calculate the components of each one of those moments about the different axes, square them, sum them, take the square root. So let's do some of the, actually let's just look at the moment about y. So do that one first, because what this is saying is we've got the y-axis. Here's green for my axis. We got the y-axis. Does this force create any moment about the y-axis, you know, kind of in that direction or that direction? And it doesn't. All of the lines of action for these forces, they actually go through the y-axis. They intersect the y-axis. So this is similar to when we were dealing with the trusses, and we would try to apply a force right at the pin or the center of rotation. There's no moment. So my, just by observation, the about point B is 0. I'm going to rearrange these again. Or, well, okay, that's how I did it before. 0. But then let's look at x and z. So if I'm thinking about the moment about the z-axis, and I'm pushing with the x force here, then you could imagine, so the fx is in the xy plane here. And you could imagine this beam wanting to rotate around with the center of rotation being at B. So we define that as B here. You would imagine it rotating around this beam, rotating, or this bar or whatever it is, rotating around the z-axis. So the force in the x direction does create rotation about the z-axis for this bar AB. It does have a length. I think I made it 21 when I worked with it before. 21 inches from point A to B. I don't think that's how many dots there are there, but that's what we drew. So that one we need to calculate. And then we think about, well, what about the x-axis? Well, this bar about the x-axis would rotate in the zy plane if I apply this force C. If I push down at A in the z direction, then this bar would tend to rotate in the yz plane about the x-axis. And so there is a rotation there, or the want to rotate anyway, the create a moment. So we need to calculate those two. So a moment, the way we're calculating, we're not using vectors or anything like that, as far as we're not doing cross products or anything. So we're saying that a moment is equal to a force times a distance. And the distance and force need to be perpendicular to one another for what we're doing. So Fx has a moment arm distance of the distance from A to B. So Fx, if I can figure out Fx multiplied times 21 inches, that will give me the moment that this force creates about the z-axis at point B. So it would give me this term over here, the moment at point B about the z-axis. So all I need to do is figure out what Fx equals. And that works the exact same way that when we did the 3D concurrent force systems and we had the cosines. All the cosine of theta x, for instance, would be the angle between the force and the x-axis. So we add all those cosines. How we did that was just the definition of a cosine. Cosine of any angle is the adjacent side over the hypotenuse. So we use that definition to calculate the cosine of theta as a whole term. We have all the adjacent sides. We have 3, 8, and 7. So each one of those corresponds with whatever axis they're lined up with. We just need the hypotenuse. So we need the length from this point to point A. And that's an easy enough quantity to calculate. This length L is equal to the square root of 3 squared plus 8 squared plus 7 squared. Technically this is a -7, a +8, and a -3, but we're going to square them anyway. So, and let's just say they're all inches. I said that one was inches, so these must all be inches too, we'll say. 3 squared plus 8 inches squared plus 7 inches squared. We do that math, and we'll get the length from point A to this endpoint out here, which is the hypotenuse in our cosine equation. So let's see, 3 squared plus 8 squared plus 7 squared, square root of that, not pi, answer is 11.04. So what that says is that this length is, pen's not wanting to write, 11.04 inches from point A to point whatever that is. Okay, so Fx, the value of the x component of this force, is equal to the force, 150 pounds, times cosine of theta x. So cosine of theta is going to be the adjacent side over the hypotenuse. For x, the adjacent side is the one lined up with the x-axis, so 8. So F is 150 pounds. We're going to sub in cosine of theta x as the definition of cosine. So adjacent would be 8, hypotenuse would be 11.04. Those are both inches, so they cancel out. And we'll have a value for Fx. And it's just 150 times 8 divided by 11.04, 108.7. The units would be, oh, well, hold on. That is just f of x, yes. So that's pounds. The actual moment, you know, what goes in here, the moment about the z-axis at point B is f of x, or not f of x, fx, the force's x component, times its moment arm, 21 inches. So fx times 21 inches. So it's just the 108.7 times 21 inches. 2,282.6 inch-pounds. Now, the tricky part on this hopefully is not the tricky part. Tricky part is this positive or negative? And when we were calculating moments before with the trusses, you know, calculating some external reaction or whatever, we just chose clockwise is positive or counterclockwise is negative. In 3 dimensions, that's a little bit tougher to even say what is clockwise. Are you looking down the y-axis? Are you looking in the direction of the y? So it's kind of confusing. So what we do is we use what's called the right-hand rule. So right-hand rule. And it literally means take your right hand, not your left hand, but your right hand. And what you do is you imagine the rotation or what direction the moment's going. So in this case, thinking about point A, we're rotating about, point B. So we're rotating about point E up B. A would go around this direction, right? You take your right hand and the fingers, not the thumb, but the fingers of your right hand and try to curl them in that same direction. So I couldn't do it this way. This is backwards from this direction. I actually have to turn my hand upside down and curl them to make my fingertips curl in this direction. And when you do that, when you line up the direction of your curl with the direction of the sense of this moment, your thumb is either pointing down or up or, well, whatever, you know. In this case, it's either down or up because we're talking about the rotation occurring, point A moving in the XY plane, right? So going this way. And my thumb is pointing down. So my thumb is pointing in the opposite of what I have defined as positive z. So my thumb is pointing this way in the negative z direction. Since my thumb lines up with the negative z direction, this moment, according to the right-hand rule, will have a negative sense with it. So this would actually be negative 2,282.6 inch-pounds. Because clockwise and counterclockwise don't really, are not easy to everybody visualize the same way, but with the right-hand rule, you get the same thing every time. So that I just wanted to go through this so you have an idea on how the right-hand rule works, how to deal with calculating the moment of a three-dimensional force about some point. To finish this out, we would still need to figure out the moment about the x-axis at point B. So y, the fy component, and the fx component do not make this bar AB want to move in a way around the x-axis, kind of like this, in the YZ plane here, move that way, but the z component does. So basically we'd take this same approach, but here we would find fz equals f times cosine of theta z. So the only number that changed would be this 8 would become a 7. And we get a slightly different force here. The moment arm for this force is also 21 inches, so this would stay the same, and we get a slightly different number here. And then the moment that this force creates about point B as a total combined moment, we would plug in this number here, 0 here, and whatever we calculate for the x, which will be similar to this number, here, square them all, sum them all, take the square root, and that'll be the total moment created about point B in three-dimensional space. So I just wanted to go over that to get started. And then now we're moving into our idea of centroids. So let's go get rid of this, get it out of the way, and talk about centroids. And I think to start with centroids, we will probably move to SolidWorks first just to get some terms down. But let's go ahead and write down that we're going to deal with centroids. Now we're going to do two-dimensional centroids pretty much actually exclusively in this course. A three-dimensional centroid isn't really going to be applicable for what we want to do with it later. We're moving into a topic now that has to do with beams versus where we were with trusses having members. It sounds like they're just different words, beams and members, but they're the same thing. We're trying to make the distinction that they are the same. They might literally be the same piece of metal, but we're applying the forces to them differently. And we're going to use beams to mean pieces of a structure that might flex or bend. And we're going to use member for pieces of a structure that only stretch or compress. They don't bend. And so they have different loads on them. So centroids are going to be the centroid of an area or a cross section. So we need to know what all these terms mean. So let's look at SolidWorks. Let's get SolidWorks running there. And there, yes, all right. So we're over in SolidWorks. We're gonna make it a new part. One typical beam cross section is called a T section, and it literally looks like the capital letter T. So I'm gonna draw something that's sort of like a T. We're not going to worry too much about the dimensions. We're not going to calculate anything with this. We're just going to kind of show things. So there's a T. Cut that little piece off there, and then we will extrude it into a beam shape. So let's make it longer, something like that. All right. So here's our, you can imagine a whole bunch of these holding up the floor in some kind of building or whatever. Another common shape, we haven't saved it. Another common shape would be an I-beam. So the end of it, instead of looking like the letter T, would look like capital letter I. Some are C's or channels, and they look like a capital letter C. There are right angle beams that look like an L. There's all different kind of shapes of beams. This is one of the relatively common ones. Probably an I-beam, the one that looks like a capital letter I, is the most common kind of beam, other than maybe just a rectangular piece of 2x4 or whatever. But anyway, here's our beam. It's got some length to it. A couple of things have to be true for the centroids that we're going to work on here in a second. So one thing is that down the whole length of this beam, it can't change shape. It can't be a square on one beam and a T on one end and a T on the other end. So it can't do that. It can't change density or weight from one end. So this end over here can't be heavier than this end over here. It needs to be more or less the same density throughout the whole thing, same shape the whole thing, and our cross section, not that one, this one, can't change. So the cross section is this little light blue, in this case T shape in the middle. That's the cross section. It is a section created by this darker blue plane here across the object. So it's this T, and it doesn't change no matter where I place that cross section. It's the same shape the whole length of the beam. It's always that little T shape for this beam. There are lots of cross sections. We can, make any cross section we actually want to make. All these different ones. We are only going to deal with cross sections that are perpendicular to the longitudinal axis. So this beam is long this way, it has a longitudinal axis this way, and the cross section that we're going to talk about is perpendicular to that. So it looks like this. So it looks like a little T. All right, so those are a couple of things. The beam can't change materials or density from one end to the other. The cross section can't change from one to the other. And well, I guess that's really about it. Those two things, as long as those are true, then we can describe this beam for some of the equations we're going to use later in terms of this cross section, whatever the cross section happens to be for the shape beam it is. So for this beam, it's a T. All right, let's go back now, not there, to here. So the centroid, it is a property of the cross section of whatever we're dealing with. In this case, it's going to be a beam. And this cross section, you could cut across this beam any direction you choose. The one that we're interested in is the cross section is perpendicular, to the longitudinal axis of our beam. Okay, it's similar. The idea of a cross section is similar to a center of gravity. Except that a center of gravity requires like a volume. It has to have weight and mass and everything to have a center of gravity. And we're only talking about a cross section, which is just a 2D shape. So the cross section is just a 2D shape, and it doesn't actually have mass or gravity or anything like that. So it's a similar idea, though, to the center of gravity. So for instance, for our T, if we were to draw its cross section, so there's without dimensions right now. We'll do dimensions later, but this is our cross section. We could cut this out of a sheet of cardboard or something and lay it down flat and try to balance it. Then we could imagine that somewhere right there is where it would need to balance. That is the that is the centroid, and it's that location that we need to define. Sometimes it's really easy. So, for instance, if our cross section was a rectangle, then we know that center of gravity is right here, and we can completely define it as this is whatever the height is over 2, so the height of the thing, and this distance would be the base over 2. So we could just do that. Or a circle is right in the center. These more complex shapes require a little bit more figuring. We can't just look at it and say, oh, well, that's so many whatever's above the base down here. We need a way to do this. And there's two ways to do this. One way, well, there's probably more than two. We're going to talk about two ways. One way to do this is through integration, so calculus. That particular method doesn't work as well or as easily with something like this that's made up of primitive shapes being rectangles and circles and triangles, things like that. The integration method is more for shapes that are kind of amorphous or whatever. So they have these curves and different shapes that aren't just pretty easy to deal with. But we're going to start there because it kind of shows how all of it works. Even the ones that are simple rectangles. It shows the idea of how it works. So we're going to start with that. So we're going to kind of start in an abstract way, run through how the calculus works, then we'll use a more common method. All right. So to get to the abstract, we're gonna not deal with something that's defined as a T or a rectangle. We're gonna use a generic shape. So first, let's put it in a coordinate system. So there's our coordinate system. And we're going to put just 3 little shapes in this coordinate system. So these little shapes could represent anything. And we could make as many as we wanted, but I don't want to write a whole bunch of letters and numbers down here, so we're going to do 3. And this will be number 1. This will be number 2. And number 3. So the idea here is that I could assemble any pattern of little red dots and clump them all together and make any shape cross-section that I want. But make it a little simpler without being cumbersome to write all this stuff down, we're just going to have 3 red dots. And each one of these dots, they are areas, but they represent remember, they represent this cross-section is representing a whole beam or whatever. So you could think of them as having some kind of weight associated with them. So I'm just going to show it as they have a weight associated with them, even though they're just an area. But for what I'm about to do, the weight might make it more sensible. Each one of these has a position from the y-axis. So this is the x-axis, so this would be x1, the distance in the x direction from the y-axis. This one would be x2, and that one would be x3. So I could clearly define all of those. So what I want to do is, remember, these individual red dots are, they're kind of like, here's one, here's one, here's one, and I could have had a whole bunch more in here to kind of represent the entire beam, right? The entire cross section of the beam. I'm only picked out 3 of them to draw. So each one of them, what I want to know is, where is the centroid if you consider all of them at one time, so consider the entire cross section. So what that would be is somewhere out there, maybe right here, is an equivalent. I'm going to draw it a different color. So it has an equivalent, in this case, weight, although in our equation it's actually an area, but I'm representing it as a weight. So it has an equivalent weight. That would just be, add up all the red dots and it would have the equivalent, the same weight. It's kind of like lumping it all into one place, right? So we'll just call that the total weight. Maybe I should have written in green to keep my thing separate. And it has some distance. I don't know. Oh, not 3. C. So it has a centroid. It is the centroid. This center point is the centroid, and it is as if you have lumped all of the red dots, however many you draw, into a single dot and placed it in the center, not the geometric center necessarily, but the centroid of this shape. How to figure out where this is. I know everything else. I know W2, 3, 1, and therefore I know the total weight. I know X1, X2, and X3. I just don't know this one. So what you do is each one of these, and this is where I wanted it to be a weight so that I can talk about maybe a moment. So this one, number 1, has a distance, X1. In this case, I won't put an I, X1. If I multiply that times W1, that's the moment, if you want to think about a moment, that this area creates about the y-axis. So I've got a force, or an area, times a distance, and there's a moment. And each one of these has one, so we could add them all up. We could even generalize it to just say that, hey, if you add up, if you take the sum of every one of the distances times their associated weight, then you would get this equation. And so you could have way more than just 3 of them. You could sum up all the one you wanted to. Or you could say, well, maybe it's not a discrete, this is a discrete way of doing it. You could say that you could do a continuous process. Ran out of room to write. That says continuous. And just do an integral. Now, we're not actually integrating over the weight, though. This weight, remember, is really just a 2D area. So we're actually integrating over the area. So I'm going to put a dA in the integral sign. So the area of this cross section. This term is actually called the first moment of area. So this integral x dA, or integral y dA if you're talking about measuring in the y direction, or z dA if we were dealing with the z-axis. That's actually called the first moment of area. All right. So this is the combined, every one of the little red dots, their combined moments, all added together. I want to replace them with the green dot. So the green dot is, in this case, W1 plus W2 plus W3. So that's the total weight times XC. So what I'm saying is that the combined effect of all the red dots, or their moment of area, that combined effect I want to replace with one green dot that has the same effect. So I set these two equal to each other. So let's just say that this would equal the summation of basically all of the W's. So summation of Wi, that term, times XC. So I want to set this equal to this because I want them to basically be replaceable with one another. So I either want to be able to think about the single green dot that's the total weight at some unknown centroid distance, or each individual dot wherever they may be. So I'm going to set those equal to each other, and I get summation of Wi times XC equals this term, summation of XI times Wi. I'm trying to use the parentheses so that we tell the difference in these, because otherwise they might look the same. This is the thing I'm looking for. So I'm just going to solve this equilibrium equation, not equilibrium equation, but kind of. I'm going to solve it for XC. And I get summation of XI Wi over summation of Wi. Now remember, these are not actually weights. They are little tiny areas. And this is just the summation of all of the weights or all the area. So this is just the total area. So there's a discrete equation that I can use to calculate the location of a centroid. I can use the continuous version. So replace the numerator with integral of x dA. The denominator is still the total area. And I can use either one of these equations to calculate the location of the centroid for any kind of shape. So the discrete one, the top one, I can use for this and just think of two shapes, a rectangle on top and a rectangle for the stem here. So I could do it the discrete one and use that. Some shape that's, you know, I don't know, some crazy looking shape. I would have to figure out the equation for this line and use the integral form. We're going to do the integral form here, but for a simple line, so not one that's got such a convoluted shape. We're going to use a triangle. So here's what that would look like. All right, so let's put our coordinate system out. Okay, and let's draw our shape. So it's just a right triangle. Let's make this a 45-degree angle. So if we write the equation of this line, y of x just equals x for that equation of that line. But you could put any shape you wanted. You know, you could write any kind of equation here to define this contour. Okay. We are going to integrate. Let's put some dimensions on here. I'm going to make these all variables, so there won't be any actual numbers in this one. We'll do numbers in a minute. Let's call this B. Let's call this H. Now in this case, since I made this a straight line that y equals x, h is also equal to b. They're the same value, right? And b is equal to h. What we're looking for is the centroid of this shape. So by looking at it, we can pretty much just guess that it's somewhere over here. Like if we were to cut a triangle out of a flat sheet of paper and try to balance it, it would balance somewhere over there. And we want to know exactly where over there it would balance. All right, so we're going to use our equation, integral x dA over total area. That is x of c. So that is this distance. So that distance is given by this equation. We're going to integrate from 0 to b, right? And what we're going to integrate, dA, this area, is this. So that is dA. And we're going to basically, you know, this is a really thin strip, and we're going to line a whole bunch of them up across here to make this triangle and add them all together. That's basically what integrating does. We're calculating the area under this curve times x. So x is just our variable measured from 0 over to b. So we're actually going to go, I guess I could put my limits on here, 0 to b. All right. dA, you probably don't know how to, you know, take the integral of x dA. So we're going to redefine dA. dA is this shape, and it has a width of dx. We're going to make it really, really thin, so a dx width, and it has a height of y of x. So the height of this, no matter where I put this strip, put it over here or over here or over here, the height of it is defined by this equation. And the equation just says that the height y is equal to x. So dA equals base of dA, which is dx, times the height of dA, which is x. And normally you're going to write that as x times dx instead of having the dx up front. So everywhere I have dA, I can just replace this with dA. The total area is equal to base times height, which I literally have as b times h, over 2 because it's a triangle. In this case, though, for this triangle that I'm working with, h is equal to b, so it's actually b squared over 2, right? So let's take this information and put it into here. So we're still going to integrate from 0 to b. X times dA is now x dx, and the total area is b squared over 2. So that's the same as integrating 0 to b, x squared dx over b squared over 2. The b squared over 2 I can move up to the front here, so 2 over b squared times the integral of x squared dx is x cubed over 3, and then I evaluate it from 0 to b. So I'll put a 0 in there and it just becomes 0, the whole thing, so I only need the b. So 2 times x, we're subbing a b, so b cubed over, there's b squared, times 3. The b cubed cancels with the b squared, and I'm just left with x sub c equals 2/3 times b. So for this setup, I can calculate, using calculus, that the location xc here is just 2/3 of this base. So however long that base is, I take 2/3 of it, measure from the same point that I did my 0, x equals 0, which is over here, measure over 2/3 of that base, and that's the location for that centroid, or at least in the y direction. I still need to know that, which we would call y sub c. So to get y sub c, I could do this same thing again. Let's see, make sure we don't get covered up there. 0 to b, y dA over the total area. I could do that, and we'll do that one. The other thing I could do is I could change dA, instead of being a strip that's in the vertical direction, I could change it to a horizontal strip and go in the y direction from 0 to h, or 0 to b, since h and b are the same thing in my triangle. Okay, there is one little thing over here to keep in mind that is easy to make a mistake on this one. What the x and the y here represent are, let's see, that goes back to here. So remember, the x is the moment arm. We're not really talking about a moment of a force. Remember, it's first moment of area, but it's the distance between that area and the reference point. So it's a moment arm. Here, the area is this little rectangular strip. So the center of the rectangular strip, somewhere in there, this moment arm, when we were in the x direction, is basically just wherever the strip is, because remember, it's infinitely thin because it has a dx width, but it has height to it. So in the y direction, this y here, let's see if we can get this, let's see, maybe green, is this distance. So this distance is that value for y. So it's actually half of the height of the differential strip when we have the strip turned vertically like this. Now if we had the strip horizontal, then it would just be y. But the x would be different, you know, because now we'd be talking about to the center of that horizontal strip. So you just have to keep in remembering that this x and this y don't represent, you know, x and y here. They represent the moment arm for each one of those little differential areas. All right, so let's carry on with that idea in mind. So equals the integral from 0 to b. Y is actually half the height, which is x over 2. dA is the same. We didn't change our strip, so dA is still x dx. AT, we didn't change the area of the triangle, so it's still b squared over 2. So we need to evaluate that. So let's take the let's do the parallel steps here. So 0b x squared over 2 dx, b squared over 2. We'll take the b squared over 2 and move it to the numerator. So that's 2 over b squared, just like it was here. There's a 1/2 built in here, so take that out. It's just a constant. And then we'll integrate x squared dx, which is x cubed over 3. And we'll evaluate from 0 to b again. So we have 2 over 2, so those cancel out. So I'm left with x cubed, which I'm going to sub in a b for, so that's b cubed over b squared times 3. And we could simplify this with b cubed over b squared is just b. So I have 1/3 times b. And remember, in this setup, b is equal to h. So 1/3 of h would kind of make more sense in the setting here. So now I know that this centroid for this triangular shape is located at 2/3 of the base measured from my reference point, which is the origin of my coordinate system, and at 1/3 of the height. So if I go up 1/3 of the height and over 2/3 of the base, that will completely locate the location of that centroid. Now this process for a triangle is a little not needed. Primitive shapes like this, triangles, rectangles, circles, half circles, quarter circles, sectors, parabolas, ellipses, all of these kind of shapes, this has already been done. So you would really only use the integral method if your equation of this profile is some very unique shape. So it would really only show up in like a homework problem or something kind of abstract, just to prove that you knew how to do the thing. What's more valuable here is digging into how these things are created, how the centroid equations are created. Because what you normally do is you normally look at something like, let's see if I can find it, something like this, that, let's see if I can get it all, there we go. Now it's getting in there. Where all of these centroids are already defined for you. Let's find one. There's a rectangle. We're going to use that one in a minute. But, well, actually, here's a triangle somewhere. At the very bottom, there's a triangle. It's not a right triangle, but it is a triangle. So there's multiples of these charts everywhere. They're all the same as far as the equations. They just might present different versions here and there. I kind of want to look at this rectangle, though, because we're going to use it in a second. So here's there's a rectangle, and it has a base b, height h. They define where the centroid is. Oh, actually, this is not a centroid. I'm looking at the wrong thing. This is a moment of inertia. It says centroids of common shapes, but oh, you know what they did? They just put the centroid right in the middle. So let's look at one that has a shape to it. Here's one that's got a centroid that's not in the middle. So they show you that the height of this thing is the height of the centroid is 1/3 of the height of the triangle, which is what we just calculated. But for a rectangle, the centroid is in the direct center of it, which is pretty obvious. You don't really have to calculate that, and that's why they didn't bother to put it. These over here these are moments of inertia, so we're not to that yet. Let's go and try to use one of these in an example with numbers, real numbers. So let's go back to our T. Remember the T cross section here? Let's go back to it and put some dimensions on it and find exactly where the centroid would be for this T cross section that represents this entire beam. So the one cross section represents the entire beam, and we'll use it later on to figure out how this beam is flexing. We'll close this. We don't need to save any of that. We don't need that or that. We just need this. All right, so our T something like that. So for naming, we're going to start having to talk about these beams and the different pieces of them. This top part is called the flange. And this piece here for a T-beam is called the stem. Okay, that's just naming convention that we'll need later. So anytime you have an axis of symmetry, which we do here, that is a good place to put your reference system. So we have an axis of symmetry right through here. Right, the left side, well, had I drawn it really neatly, then the left side and the right side would be symmetric about this axis. That's a good way to put, or a good place to put one of your axes, because as soon as I do that, I automatically know that XC, the location of the centroid in the X direction measured from the Y axis, is 0. Because I know the centroid of this shape, just by looking at it, it's, it's somewhere right here. I don't know exactly where, but it's somewhere right there, laying on that axis. Now, if you're working a problem, like a homework problem, you have to deal with whatever coordinate system they've given you. So it may not be right through them. Then maybe they put it over here or up here or wherever, and you have to measure from that in order to get the same numbers that that particular problem is trying to get. We'll put the x-axis down here, and how you work with this is you are trying to find primitive shapes like rectangles, and here I have 2 rectangles. So this is a really easy one. This is about as simple as you can get other than just a single rectangle. So I'm going to say that this is one rectangle and this is one rectangle. Let's get them colored so we can tell them apart. So the flange is created by one primitive shape, which is just a rectangle, and the stem is created by another rectangle, like that. And you can have as many of these pieces, these primitive shapes, stuck together as you needed to create your shape. Next time, we will do one that's way more complicated, that has multiple pieces. Some of them are cutaways, some of them are not just rectangles, and we're just going to do something relatively simple right now. So the integral method, integral of y over a, doesn't really make sense for this. I'd have to come up with an equation, but the discrete method, where, let's see if we can find our picture. Here it is. The discrete method, summation of ax over a, that one kind of works here. So y sub c is equal to the summation of all the individual areas times their y coordinates, their moment arm for their own centroid, divided by the total area. So this equation, with just 2 pieces, it's simple enough to just plug them into the equation and work it that way. I'm actually going to build a chart down here that makes it simpler when there are a lot more than 2 pieces. In my mind, it makes it simpler. It might always be simpler for you to just use the equation. I'm going to show you how to use the chart. So how the chart works is you define all your shapes. And so I have 2 shapes, 1 and 2. I usually draw a little picture to remind myself which one is which. So shape 1 is the flange on top, shape 2 is the stem. Each of those shapes has an area And to calculate that area, we need to put dimensions on here. So I'm going to make this, make that dimension 2 inches. Let's make that one 8 inches. Let's make that 1 inch. And let's make across the top here 12 inches. So we have all our dimensions now. So the area of shape 1 is 2 times 12, 24 inches squared. The area of the green stem, 8 times 1. So there's my total area right there. Right? So I just sum up the columns. The other thing I have an area, I need the individual Y components. So what I normally do is I go in and I pick out the centroid for each part. So this distance would be Y, this is part 2, so Y2. This distance would be Y1. This is what I'm after. That would be YC. So YI measured in inches. Y1 is, we start at our reference point, which is the x-axis for the Y measurements. So 8 plus 1, 9 inches. Well, I've already got the units in there, so 9. For part 2, the distance from the x-axis to the centroid of part 2, just the green shape, is 4. Okay, now I need to create this numerator, a times y. It'll have units of inches cubed, so it's not a volume, it just has those units because you're multiplying an area times a distance. Normally, remember, this is a moment, but it's first moment of an area here, so it doesn't actually end up with inch pounds or something. So 24 times 9 is 216. 8 times 4 is 32. I need to do the summation of a times y. So 248. And then to calculate y sub c is the summation of a times y, which is right here. This is the summation of a times y. So 248 inches cubed divided by the total area, which is right here, 32 inches squared. My units are going to work out. They're going to be inches cubed over inches squared, which would just be inches. So 248 divided by 32 is 7.75. And that tells me that from the same reference, so from the x-axis measured up to the centroid of the whole shape, if I go up 7.75 inches, I've found the centroid of the whole T shape. And that's what we're usually going to mainly use this method here. Or you can use the equations. We're not going to have to do the integral method on most of the shapes for these beams because the beams are normally made of rectangles and maybe a triangle here or there, or maybe an arc or something like that. But they're going to be these primitive shapes that we have charts that tell us the centroid for. So 4r over 3 pi is the location of a centroid for a half circle. You know, so we're going to have that kind of information for the shapes that will compose our shapes. So we'll have some composite shapes made of primitive shapes. We'll do that next time. I think for today we are probably good on getting these centroid ideas across and started. And tomorrow we'll come back and start with some more complex composite centroids. So they have to figure out how to combine more than just 2 rectangles together. But we'll use this exact same process. I like the chart because it's I don't know, it's easier to keep track of all the little individual pieces, whereas these equations, when you have 5 or 6 primitive pieces you're putting together, can get you can get lost in just a long string of multiplication and addition. So I like this chart better. All right, we will be back tomorrow at noon, and we will look at more centroids. See you then.